So I prepared some questions for us to go over, some example problems. And if anyone has any additional problems they would like to discuss, let me know. So we have a number of new reactions that we covered last week that you might see on this week's exams, tomorrow and Thursday. So I put down some examples relating to some of the major themes that you want to be prepared for. So, looking at this reaction here, I want to do a synthesis here, so maybe number the carbons. So I'm seeing that there's an alkene here, and I have the same alkene here, or at least maybe it looks like the same. So maybe I want to start numbering here in such a way that gives those two carbons the same numbers. If these four carbons here are the same as the four carbons on the product that I've labeled with the same numbers, then the goal here is going to be to connect four more carbons. So we have to figure out how we're going to do that. And in the process, it's going to make a bond between carbon 1 and carbon 5. So if we want to make a new carbon-carbon bond, we're going to have to probably make one of these carbons a nucleophile and the other electrophile, right? So just to remind you some of the major ways to do that. One is the Grignard. That's a great nucleophile. The Grignard will attack. We can get it to attack an electrophile if it's a carbonyl, right? Come in there and attack. That'll make a new carbon-carbon bond between the R group and the carbon of the carbonyl. We could also have a Grignard attack, as long as it's a primary site, an alkyl halide, where the halide would be the leaving group. And that would make a new carbon-carbon bond there, where the R group would then connect to that primary carbon. Can't really work if it's secondary or tertiary, because then the Grignard would be more likely to act as a base and pick off the proton here to make an alkene while pushing out the leaving group. And then the third major one that we talked about the Grignard with is where it'd be attacking an epoxide, and that was a while ago. We haven't seen that too much lately, but that also works because of the ring strain opening, makes it a lot more stable. And when we talked about this reaction, we said if you're looking at the products, if the new carbon group is added to the same carbon where there's an oxygen, that usually results from a Grignard. If it's added to a carbon that's one away from the carbon with the oxygen, that can often be done with an epoxide. More recently, though, we've been talking about enolates as nucleophiles. Right? So if I have a carbonyl and an alpha carbon, and I'm able to remove a proton from that alpha carbon to make a carbanion that's stabilized through resonance with the oxygen, that's a great nucleophile. That can also attack any one of these types of electrophiles in the same way. But then last time when we talked about this specific distance between carbonyl compounds, we said if you can get two carbonyl compounds in your product that are 1, 2, 3, 4, 5 atoms apart, that's usually an indication that the carbonyl, or the nucleophile, is attacking an alpha-beta unsaturated compound. Because if that attack occurs, which would push electrons up to the oxygen, This carbon here now connects to this one. So this would be the new connection made by this arrow. These electrons move here. These electrons move up to the oxygen. And then typically there's a second step where some H3O plus is added, and that will donate a proton to this carbon here, which will give you the carbonyl back. Right, so now I have CO double bonds, and they're 1, 2, 3, 4, 5 atoms apart. So when you see that pattern, you want to think about getting an enolate or an enolate type nucleophile to tack an alpha beta unsaturated carbonyl. So I could imagine that occurring here if this structure is converted into the enolate, because there are some alpha protons here that could be removed on this side. So you're not going to remove an alpha proton here because if these electrons, we'll just imagine if that did occur, if some kind of base picked off this alpha proton and these electrons stay behind, that would produce this. This is not nearly as stable as an enolate because it's not stabilized by resonance. Right? The p orbital overlap doesn't involve these electrons, which means these electrons would have to be in an sp2 orbital, and while that's relatively compact and held closer to the carbon's nucleus than an sp3 or a p orbital, it can't be stabilized by resonance. Right? So we need the lone pair on the alpha carbon to be in a p orbital so it can overlap with the p orbitals of the CO double bond to stabilize that through resonance, and which is really what allows the negative charge on the carbon to be stable enough to be able to even really exist or form for any period of time. So we're not going to do that. We can't pick off an alpha carbon if it's part of a pi bond, or I should say if it's vinylic, because the resulting lone pair wouldn't be well stabilized on an sp2 hybridized carbon. So if I add a base to this, this is the only proton that could be removed. So really I've got two options here. I could add a very strong base like LDA. If you recall, LDA has a negative charge on a nitrogen. And so that's really a lot less stable than a negative charge shared between an oxygen primarily and a carbon through resonance. So that usually produces enolates in a forward-only equilibrium. The other option would be to use something a little bit less reactive, which might be cheaper or easier to handle. Maybe it's like NaOH or methoxide or ethoxide. DOH minus would pick up the same proton, but in that case, DOH minus is very similar, and OR minus would also be very similar in stability to the resulting enolate. So this would produce an equilibrium that would have significant amounts of substance on both sides, not necessarily equal amounts, but the pKa of the alpha proton is very similar to the pKa of water, so those two sides are similarly favored in the equilibrium. And in this particular situation, it could work either way. Because if I convert all of my reactant into this enolate, then I can make the product by simply adding the other four carbons in the form of an alpha beta unsaturated compound followed by some H3O plus, and that would go through the mechanism we saw down here where the enolate would attack the beta carbon and push electrons up to the oxygen, and then the H3O plus would just protonate that. It wouldn't protonate the oxygen. Let me insert something in there to clarify that. So once this attacks oops. You'd have these electrons swing over to make the pi bond, these would swing up to make a negative. And that would be the structure you would get. So these electrons would swing back down in, and these would pick up a proton from an H3O plus. And that would give the product. Anyone who's on the live feed, does anyone see a problem with that? This part right here? Is there any issue with that anyone can see? Yeah, so that's a good point, Amy. We could also imagine this oxygen, instead of pushing down and having the pi electrons here pick up the proton, it could just pick up the proton, which would give this product. Then the proton would be on the oxygen. But that's not really an issue because these two substances are already going to be in equilibrium, right? So the ketone and the enol tautomerization is unavoidable, and even a small amount of acid or base would ship that back and forth until it reaches equilibrium. And since the CO double bond is significantly more stable than the CC double bond, it should favor the keto form. So whichever oxygen picks up the proton, eventually it's going to end up on the carbon to produce the ketone rather than the enol. Akua says, could the water cleave? Cleave where? I'm not sure which water and which cleavage you're talking about there. So Akua is typing while we're waiting for that. I mentioned that the issue I was thinking of here, which is a problem in producing the product we want, is there's a competing attack where this lone pair might also attack the carbonyl. So we'll look at that in a second. So let's see. Akua writes, can the water attack the keto and break it apart again? Yeah, so you could imagine a water or some other nucleophile attacking here and breaking this open because the resulting negative charge would be stabilized by resonance. But then the water would probably get pushed back out by this enolate. It would probably come back in and push that out again, since the water is such a good leaving group. And water is really quite stable on its own. So that could happen, and it might produce some undesired side product, but probably once everything reaches equilibrium, that would be a minor situation, a minor side product. So this attack, though, when we were talking about this last week, we said a typical enolate is a pretty strong nucleophile, and there's a pretty large amount of partial negative here, and there's a lot of partial positive here compared to way out here. So there's a greater charge attraction for the enolate to attack at the carbonyl, but if it does so, it produces an intermediate that's not stabilized by resonance. So that's why I normally would think it would to attack the beta carbon of the alpha beta unsaturated carbonyl to give this intermediate. But to get more of the structure to attack where we want right here versus where we don't want in this particular case, we really need to stabilize the enolate more than it is, because an enolate is a strong enough nucleophile to attack often at the carbonyl carbon, similar to how a Grignard attacks very readily at the carbonyl carbon. So if you put this route down as your answer, that would be reasonable. I think I've got the same issue here, whether I make the enolate with LDA or NaOH. I want it to attack the beta carbon, not the carbonyl carbon, and that's not easy to control when I have a strong nucleophile like an enolate. So rather than forming the enolate, we could go with the Stork reaction. So let's talk about that option. So the Stork reaction is still going to make an enolate type situation. It's just not going to be exactly the same. So in the Stork reaction, what you would do first is to use a secondary amine and some acid catalyst. And the oxygen here is going to pick up the acid catalyst. The secondary amine, we need two R groups there, doesn't really matter what they are. It's going to attack the carbonyl, push these electrons up. So you'll get an OH here. And then that nitrogen will be there. Then this nitrogen will be deprotonated. So another amine would come over and pick off this proton to balance out that charge. And then this oxygen once in a while would pick up another proton from a protonated amine or from the acid catalyst to become a good leaving group. And then this nitrogen would shift its electrons in there, push that leaving group out. That would give then a double bond between the carbon and the nitrogen. And then typically another molecule of the amine would pick up this proton and push electrons up to stabilize that nitrogen. And that gives an enamine. And in the Stork reaction, an enamine has a slight partial negative here. And so this carbon, just like an enolate would be, is nucleophilic, but it's much less nucleophilic. It's not nearly as strong of a nucleophile. So since there's very little partial negative here, there's not very much of a chance that that'll attack directly at the carbonyl carbon, which is the problem with the enolate attacking, the main problem. So what would happen here is the lone pair would help push in there to push these electrons out, and then that attack would occur. So instead of forming this structure, the attack would occur there, and we would have, oh, I gotta redraw this. All right, so let's draw the structure here. So now we've reformed this, which is not too unstable to have a nitrogen with a positive. This carbon here is going to be attacking that one. So it's going to be connecting there, pushing electrons over here and up onto the oxygen. So in terms of the synthesis, the Stork reaction would first involve adding some H plus and a secondary amine, followed by some H3O plus and water. And the H3O plus and water will do the same thing it was supposed to do before, which is to provide our proton. So when these electrons swing back down, this can pick up a proton to reform the CO double bond part of the structure there. But H3O plus and water is also, oh, well, I should insert something in here first. So before we break this up, we have to also add this structure, right? So can't forget to draw that in. So then third would be H3O plus and water. And so just to recap, the proton and the secondary amine get us to the enamine structure here, right here. This is the enamine. Then we would add this in the second step. The enamine would attack it to give us this intermediate. Then we would add water and H3O plus in the third step. That would swing in and pick up a proton to produce a CO double bond here on carbon 7. And the H3O plus and water are the conditions we need to break this and reform the CO double bond there. So let's just recall that mechanism. So the water, since this is already positively charged, will attack here, push these electrons up to the nitrogen. I'm just going to draw this half of the structure. So the rest of the structure I'll just call R. So this whole thing right here is what we're calling R. R is connected here. So these electrons swing up to the nitrogen. And a water has attacked there. So then a water would deprotonate this. Another water would come in and pick off this proton. Then the nitrogen would pick up a proton from the H3O plus. That would become protonated, making it a good leaving group. So then this oxygen would swing its electrons in, push that out. Now I have a CO double bond there. And so the product would be produced there just by removing that proton with the water. So another water would pick off that proton, electrons would stay behind and give the product. So the Stork reaction is pretty convenient. It's not that many steps. It helps to produce a relatively weak nucleophile that's going to more reliably attack the beta carbon and give a compound with CO double bonds that are 5 atoms away from one another. So that's the key pattern there. Any questions about that one? All right. The next one I put here is another quick synthesis problem. So I would approach it, I would start it the same way, looking at numbering the carbons, trying to see which carbons in the reactant line up with the same carbons in the product. Yes, Amy, that's a good question. So just to backtrack real quick here, in this step here, you would add excess, and that's typically the case when you add H3O plus and water. But in this case, especially because converting this iminium ion into the product is a reversible process. And since water is a reactant in that process, adding excess of it helps to shift it toward the product side. So that would be excess, although if you didn't indicate excess, I wouldn't probably take off of that because that isn't something I think they necessarily make note of when they discuss those reactions in the textbook. But yeah, you definitely want it to be in excess. All right, so in this next one, we've got 3 more carbons we need to add beyond the first 4 there. So I need to add a 3-carbon group. In this particular case, again, I can see a connection between 4 and 5 that needs to be made. And we just saw an example where we can make 4 into a nucleophile, so we would just have to be able to get it to attack 5. So here in step 1, convert this to the nucleophile. So we talked in the last one, maybe LDA would be a good choice, because that would be strong enough to shift all of this into the enolate product. And there's only one site where the enolate can form and be stabilized by resonance, as we described. So that would be LDA. And then in step 2, we want to figure out what 3-carbon group to get that to attack. So your instinct may be to add a 3-carbon group with the leaving group, like a bromine or an iodine or a chlorine. If you did that, though, when this comes in to push out the leaving group, you're going to add the 3 carbons you need, but it's not going to be easy to form a double bond there. That could work. We'd have to form a double bond there, though, and so one way to do that would be to add 1 equivalent of like a Br2 and NaOH. That halogenation reaction, as long as we don't use excess, it won't replace every alpha hydrogen with a halogen. If we just use 1 equivalent, then it won't be the cleanest reaction, but we can potentially replace one of those protons with the Br. And then we could form the pi bond there by doing an elimination reaction with an ethoxide or terbutoxide or methoxide. Those should be sterically bulky enough to pick off this proton and push electrons in, push out the leaving group, and make the pi bond where you want it. So that's one option. Probably not the best option. As I said, this reaction isn't really reliable if you're trying to only replace 1 alpha proton, because when some fraction of the reactants have a bromine connected there, that makes the next hydrogen more susceptible to bromination, because now that I've got some of this formed and some of this remaining, and they're both competing to react with the remaining Br2, my goal is to get all of this reactant into the form of the products to get a clean, high yield, and then keep going. But when they're competing now over the remaining Br2, picking off this proton with the NaOH to produce an enolate that's stabilized through resonance and induction is going to happen more often than picking off this proton, because the enolate's only stabilized by resonance. So once some product forms there, it's more likely to pick up a second bromine than the reactant is likely to pick up the first bromine. So it's hard to get all of this reactant converted into the product with only 1 bromine attached, because I only want 1 leaving group to then produce the product. So that's a method that could work, but it's probably not the ideal way to make this product in the most efficient, highest yield. So instead, I'm going to add 3 carbons here. Instead of adding the 3 carbons with just a leaving group, I'm going to add the 3 carbons with aldehyde. Right? This is also a great electrophile. My strong nucleophile can attack it quite readily, push these electrons up. So the second step would be propanol. When that attacks, pushes the electrons up, I get something that now looks like this. So here's my attacking site. It's attacking that carbon, so it's connecting to that carbon. When these electrons get pushed up, I'll get an O minus there. So now I've got the 1, 2, 3, 4, 5, 6, 7 carbons I want. I just need to get rid of this oxygen and make a pi bond between 4 and 6, which can be readily achieved by adding some H3O plus and heat. So that would be the third step. So the H3O plus would be protonated, or I'm sorry, would donate a proton to this oxygen. Then that oxygen is still partial negative. It would pick up another proton from a different H3O plus to make a water leaving group. That could leave, producing a carbocation. And then a water would pick off this proton. Since that'd be the best base around, there's water forming here as a leaving group. That water would pick off this proton, push electrons in, and form the pi bond. Right, so this is basically an aldol reaction to get to here. That's these first two steps, aldol reaction, followed by an elimination of the OH. And it's always going to form the pi bond on the side that's conjugated, because that'll make a more stable molecular orbital for the electrons that exist in that pi bond. So we got an aldol followed by a dehydration, which is an E1 elimination in the presence of an acid. That'd probably be the best synthetic route for that, given what we've learned. Any questions about that one? All right, this next one's pretty straightforward. Hopefully someone is seeing a route for this. Any ideas from anyone here? Yes, Grignard. All right, so I got the same starting reactant. I still have to add 2 more carbons, but here I'm noticing those 2 carbons add to carbon 3, and that's clearly going to push electrons up. So as we were saying last week a lot with these alpha beta unsaturated compounds, is that the resonance, there are multiple resonance contributors here. So one would involve electrons just swinging up. And that would create a carbocation there. And that's a minor contributor. Another minor but significant contributor would occur if those electrons then shift over. And that gives a carbocation on the outside. So even though these 2 are minor, they do contribute a lot to how much partial positive exists on these 2 carbons. So due to resonance, the end carbon, which is the beta carbon, and the carbonyl carbon would have equal amounts of positive, but there's also induction from the oxygen pulling electrons up, so that's why I get more partial positive on carbon 3 than on carbon 1. So as we were saying last week, if I have a weak nucleophile, I would expect it to attack here, because pushing electrons in and attacking there is going to give me a resonance stabilized intermediate. After the weak nucleophile attacks, I get an enolate that's stabilized by resonance. If I use a strong nucleophile like a Grignard, if it's got a lot of negative, then the odds are it's going to collide more often at the carbonyl carbon because there's a greater quantity of partial positive there to attract it in. And that's exactly what we want to occur in this reaction. So the specific Grignard we would use would have the two new carbons we need to add connected to a magnesium. And that should readily attack the carbon with a greater partial positive, which will initially produce a negatively charged intermediate that's not stabilized by resonance. And then a little H3O plus and water just to permeate that oxygen. So the steps here would be 1, the vinyl magnesium bromide, and 2, H3O plus and water. So you do want to practice enough to the point where you're aware how strong does a nucleophile have to be for it to be more likely to attack the carbonyl carbon versus the beta carbon. So you want to remember that Grignards will pretty reliably attack the carbonyl carbon. Enolates that are only stabilized through resonance with one oxygen actually produce a mixture, and that's why they're not very useful when reacting with alpha-beta unsaturated carbonyls, because it's hard to control which site they go to. I get a mixture of two different attacks, and then I get these different constitutional isomers formed. It's hard to separate them. It's not a clean reaction. So if I can stabilize this enolate by adding another electron withdrawing group, either maybe withdrawing electrons strongly through induction or through resonance, maybe another CO double bond or a nitrile, a CN triple bond, something like that, to stabilize those electrons, then I can much more reliably expect that to attack the beta carbon. And that's called a Michael addition. Or in the case of the reaction we just saw up above, the Stork reaction. Any questions about any of that? All right, so I put together this behemoth for us to practice as well. So I might as well go through this one, starting in the upper left. So here I have a compound. There are two alpha carbons. If a proton were removed from this carbon, the enolate would only be stabilized by resonance with one oxygen. If a proton were removed from this carbon, then the negative charge would be stabilized through resonance with both oxygens. So if I do add a base, I expect it to pick off the proton that produces a much more stable conjugate base for this compound. So that's going to pick off that proton. Normally, we said an OR is not strong enough as a base to convert all of the reactant into an enolate. But in this case, since the reactant produces a doubly stabilized enolate through two resonance contributing oxygens, that should be a complete reaction. So this oxygen here, you should expect OH or OR to be strong enough to remove a proton from pretty much every molecule if the resulting enolate is stabilized on two sides, with resonance on two sides. And then we would expect that to attack this propyl bromide. And since it's a primary carbon, there shouldn't be too much steric hindrance to push out that bromine. So after those two steps, the product would have added to it a propyl group. It's these 3 carbons here that become these 3 carbons here. All right, so maybe we'll finish off this top sequence here. So how do I convert this into this? Well, now I can see I want to add 3 more carbons again, but I want this aldehyde at the end. Right now there's a proton here. Right, the rest of the structure is not changing. I still have the ester over here, the acetate group here, the 3 carbons of the propyl group are right here. I just need to replace this hydrogen with this group. So to do that, I'm going to again use a base to remove the hydrogen. I should pick off that proton. Making that annihilate. So what your instinct may be, I see students do this a lot, is to try to do what we just did. And if you try to add the propyl group with a bromide, and also include the aldehyde on the other side, then you have a problem, because there's pretty much an equal likelihood for the most part that this phenolate will attack here and push the bromine out, as it will attack here and push electrons up to the oxygen. It can readily attack both sites. The bromine's a better leaving group, so that makes that attack happen pretty readily. But this carbon has a lot more partial positive because of the resonance and induction, and oxygen's more electronegative than bromine, pulling electrons away, so that will attract the negative in there as well. So we'd get a mixture of products. Some of the products would be attacked where we want and leave the aldehyde group there, and others would result from the attack at the aldehyde, which is not helpful. So rather than do that, rather than have the bromine there, I want to keep the aldehyde, but we'll add an alkene here. Oh, I have too many carbons in my chain. I had 4. Sorry about that. Should have counted those up. I have to redraw that. This is 1, 2, 3 carbons. There we go. 1, 2, 3. Right, so if we were talking about explaining why that other one wouldn't have worked, I just put in too many carbons in the chain. So I could imagine this attacking and kicking out the bromine, but it also will readily attack here, so I'll get a mixture of products, so I don't want that. And if I have a nucleophile, I don't want 2 different electrophilic sites where it could attack, because then I'm going to get a mixture. I want the ability to control which electrophilic site is attacked. So I want to keep this aldehyde here and prevent the nucleophile from attacking it. But now, as we were saying a minute ago, since this one is doubly stabilized, there's not really much partial negative on this carbon, because the oxygens hold the majority of the negative charge due to their resonance and ability to stabilize negative better than carbon. So the amount of partial negative that's on this carbon is quite small. The amount of partial positive here is pretty large, but the negative is small enough where it won't be strongly pulled in there. It'll be more likely to go through a pathway where it collides here, not because it's more strongly attracted there, but because the resulting intermediate will be stabilized by resonance. So that is going to give something that looks like this. Right, the new connection between this carbon here and carbon 1 of that aldehyde, alpha beta unsaturated aldehyde. It's going to push the pi bond between 2 and 3. Oops, put the pi bond in the wrong place. There we go. Never hurts to number the carbons. put the pi bond between 2 and 3, and then electrons swing up to the oxygen and create a negative there. So then to produce a product, all it's going to have to do is swing back in and pick up a proton. So in step 2, I'm going to add this aldehyde, and then in step 3, some H3O plus and water to provide a proton for the compound to pick up. And when the electrons swing back in to reform the double bond, and carbon 2 picks up a proton, so it has 2 instead of 1, that will give the product. So please feel free to jump in anytime you have questions. So that completes the top row there in our reaction. So the next reaction step is here, and from this compound to this one. So what am I seeing? The difference is here. Well, basically I'm kicking out an ethoxy group and replacing it with an OH. And so to do that, I would use NaOH and water. That's a hydrolysis reaction. I'm hydrolyzing this ester to convert it into a carboxylic acid. When I do that, I'm going to have to use H3O plus in a second step, and that's to provide this proton. Right? So I don't really have space to go through that whole mechanism. But what would happen first is the OH minus would attack, push electrons up. It could also attack over here, but here there's no leaving group. So if the OH minus attacks here and pushes electrons up, they would just swing back in and push the OH minus back out. So I don't have to worry about that being giving me anything that would start to accumulate at an equilibrium. But if the OH minus comes in here and pushes electrons up, now when the electrons swing back down, they can push out either the OET or the OH leaving group. If they swing back out and push out the OH, it'll just go back. Now shift back and forth. Eventually, once in a while, it'll push out the OET. And that will form a carboxylic acid. But it won't stay that way because the OET that left is a nice strong base. It'll pick up this proton. And so that's why we need the H3O plus in a second step to put that proton back on and produce the carboxylic acid group there. If you have a carboxylic acid, that's 1, 2, 3 carbons away from a CO double bond. The heat, if you simply heat that up with enough temperature, the heat will shift that equilibrium toward a substance that has more entropy. And we know heat increase in temperature always magnifies the T delta S term, shifting the thermodynamics or the equilibrium toward the side with more entropy. So what's going to happen here is a decarboxylation. And that basically means we're removing the carboxylate group. So the way that works is this bond has to rotate. It would normally rotate anyway because the large partial negative here is going to attract the proton of the carboxylic acid group. So what happened here is a pericyclic reaction. The reactants circle around in a ring. So this pair of electrons here is going to swing out here and make an OH bond. This pair of electrons here is going to swing and make a CO double bond. But we have to avoid a 5-bonded carbon, so at the same time these electrons are going to swing in here. And that is going to initially give an enol, and the rest of the structure forms CO2, and that's what drives the reaction forward. Production of the CO2, which has a lot of entropy in addition to the other structure, converting one molecule into two, increasing the entropy, driving the CO2 off as a gas so it can't come back in and really do the reverse reaction. So this reaction is pretty effective. It produces an enol, which then tautomerizes to the keto form. So we got 1, 2, 3, 4, 5, 6 carbons there. 2, 3, 4, 5, 6. And we're going to have a CO double bond, one away from the end. Once this pi bond tautomerizes, right? So the pi bond is going to pick up an H plus from some trace amount of acid potentially. Then a water will pick off this proton, electrons will swing in and form the double bond. So in essence, we just removed this carboxylic acid group. It's the same structure here. You can number the carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We just basically removed that carboxylate group. All right, working our way through here. Next, we're going to add LDA. So here I have a situation where I've got an alpha proton on carbon 3 and on carbon 1. And so I have to recognize that the LDA has these isopropyl groups specifically to create a lot of sterics. That enables the LDA to selectively react more often with alpha protons that involve less sterics because they're out on a methyl group versus a more sterically hindered secondary or even more sterically hindered tertiary carbon. So we expect the LDA to react wherever there's less sterics to produce an enolate that is less sterically hindered. And then if I add this in a second step, I expect the enolate to attack there and push these electrons up. So that would give me this structure. Actually, a little differently here. Start over here. I'm going to count these up. So I got, we'll count from this side. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So carbon 2 has a CO double bond. And carbon 1 is connecting to, let's call it 7, 8, 9, 10. So carbon 1 is connecting to 7. Then we got 8, 9, and 10. And carbon 7 has a CO double bond, so when electrons swing up, it's going to become an O minus. If we add H3O plus and heat to that, we get the same 10 carbon chain. Oops, made a mistake when I drew this. Oop, no I didn't. I'm making a mistake now when numbering it. Make my numbering system match. I started here with carbon 1, so that'll be here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I did miscount it. 10. That's my fault, obviously. So that's how the structure should have looked if I had been a little bit more careful when drawing this. So what's happening here is a pi bond's forming between 7 and 1 because of the H3O plus and heat. Right? So the H3O plus protonates this twice, makes it a leaving group, and then a water would pick a proton off of carbon 1 to swing those electrons in and form a pi bond between 1 and 7. And I probably followed through with that mistake here. Let's count these. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there should be an extra carbon here. And that means there's probably an extra carbon there. Okay, so then how do I get from this structure to this one? Any ideas on what reagents we need here? Make this box a little bigger to get from here to here. So what's happening here, feel free to type something in or speak up if you want, is I've got two R groups. Basically, that I'm adding across this pi bond. And I'm making two new carbon-carbon bonds in red here, at 1 and 7. So if I want to make a new carbon-carbon bond, I need one carbon to be the nucleophile, one to be the electrophile, and I need the nucleophile to attack the electrophile. So if I look at this molecule as it is it currently looking like a better nucleophile or electrophile? Well, currently an electrophile, because the electrons can swing up here. That gives carbon 2 a large partial positive, making it an electrophile. But then these electrons can also swing in, so carbon 7 is an electrophile. So if I use a strong electrophile here, it'll attack carbon 2. That's not what I want. I want carbon 2 to remain with the CO double bond. What I want is for a 2-carbon group to attack carbon 7. So if I try to use a Grignard with the 2-carbon group, it's going to attack carbon 2 because of the large partial negative, large partial positive attraction. It's too strong of a nucleophile to get it to attack the beta position of an alpha beta unsaturated carbonyl. So instead, I'm going to use the Gilman reagent. So the carbon group I want to add has 2 carbons, so it'll be an ethyl. And I need 2 of those connected to a copper with a lithium spectator ion. And then that copper is more electronegative than magnesium. It's not more electronegative than carbon. So the carbon still attracts the electrons and creates a partial negative, but it's a much smaller quantity of partial negative. And so rather than attracting it into the carbonyl, it'd be more likely to go to the beta carbon, to go through an intermediate that's stabilized by resonance. So if I draw that intermediate, now I've got these electrons, oops. So I've got 1, 2, 3, 4, and then the carbonyl. 1, 2, 3, 4, and then the carbonyl. So when these electrons come into 7 and push, it's going to push all the way up to the oxygen. And the alpha group is coming in now and is connected to 7. But now what I've made is a resonance stabilized intermediate. So if this had attacked the carbonyl carbon, the intermediate would not have been stabilized by resonance. So it goes through a higher energy pathway. That's what makes it less likely. But this intermediate is an enolate. So if I want to connect 3 more carbons, I just need to have the enolate attack a 3-carbon molecule with the leaving group. Right, so this is really nice 1-2 punch, so to speak. We have a weak nucleophile attacking the beta carbon, and then that produces an intermediate that's nucleophilic at the alpha carbon. So we add the nucleophile to react with the electrophilic site. That makes the molecule into a nucleophile, so then we just add another electrophile, and the electrons swing in and push that out. This does have to be primary, though. It can't be on a secondary or tertiary, or it would end up doing an elimination rather than a substitution of the leaving group. But that will then add the 3-carbon group here at carbon 1. So then finally, what are the reagents I need to convert this ketone into an imine I need a primary amine and some acid catalyst, and that's from chapter 20. Any questions about any of that? So I wanted to include a question that involves the technique of adding a substance dropwise to avoid it reacting with itself. So I just want to explain that real quick. So, generally if I have a reaction going on, I start with lots of units of the reactant. Because normally I'm not worried about the reactant reacting with itself. If I have another reactant, we'll just call this X, and I add X, if I start with a whole bunch of X, if X can react with itself, that could be an issue. If I want X and R to collide, but X and X are capable of reacting together, then they're also going to collide together often. And so that's a problem. So the dropwise thing here, basically what we're saying is, if I add this dropwise, I'm not so concerned about X reacting with X anymore, because as soon as a drop of it hits and it disperses, they're going to be immediately surrounded by the other reactants. And it's very unlikely they'll collide with one another if there's only a tiny bit of that in there and it's surrounded by lots of excess of the other reactant. And that's an issue specifically with enolates, because if I have an enolate present, or a compound that can form into an enolate, like this one here, just for example, this compound has an alpha proton here, it has alpha protons here. So whichever alpha proton is removed, let's just say we remove this one and convert that into an enolate by adding a base. Well, then that, if that happens in an equilibrium and there's lots of molecules around, I'll have lots of these around and lots of these around, and there'll be a decent chance that this comes in and attacks here. And we said that's a strategy. If I want that attack to occur, I can do that. That's great. But if I don't want that to happen, maybe I want this to attack some totally different electrophile. The strategy would be to start with the electrophile and start with the base that's going to make this into an enolate. So all the conditions are there for this enolate to react as soon as it forms. Right? I've got the base that's going to convert the ketone into the enolate, and then the electrophile already there for the enolate to attack. As long as the base and the electrophile don't react, that's okay. They'll both be there. The base will convert it into the enolate, and it'll be ready to attack the electrophile right away, rather than having the opportunity to attack another one, because this thing is going to be added dropwise to avoid any high concentration of it that would cause these collisions. Right, so that's the strategy here. I wanted to explain that and the reason behind it, so if you see something like that, you won't be surprised by it. All right, so the idea here is, in the first step, I'm adding this aldehyde and NaOH. What do I expect to happen? Well, in this case, I don't expect anything to happen. So it's very rare that in the first step, what we're adding isn't really even expected to add with the other substance or react with the other substance. Right? This OH minus could come in here and push these electrons up, but there's no leaving group, so they would just swing back down and push it back out, and so I would just basically still get this reactant. There's no alpha proton here, there's no carbon here, there's no alpha position here. So if there's no alpha proton, I don't expect NaOH to pick off any protons here and make an enolate, so really there's no reaction. But the NaOH is ready to go. And this is ready to be attacked. So as soon as this compound is added, then I just have to decide which side alpha protons are going to be picked off from. Which enolate is going to form? Is it going to be the one on this side or this side? And since I'm adding this dropwise, as soon as it hits and the NaOH reacts with it, this is already in there in a large amount, so it's ready to collide with the electrophile we want it to collide with. Right, so that is the strategy. So which alpha proton is going to be removed? Well, if I used LDA, it would remove the one that's less sterically hindered. So I'm using NaOH specifically because it is smaller and it can access either one of these protons. So to know which one it reacts with, I have to compare the results of those reactions, the pathway and the intermediate through which those enolates will form. So if we look at A versus B, if the NaOH picks off this proton, electrons would swing up to the oxygen. During the transition state, the OH minus would start to form a bond there with that proton. That bond would start to break with the carbon. Electrons would start to swing in to form the pi bond. Electrons would start to swing up to the oxygen. And the rest of the structure would be here. Versus if the OH minus were to pick off proton B, we would have the OH minus starting to form a bond with this proton. That bond would be breaking. The electrons would be swinging in here. And these electrons would be swinging up there. So which transition state is lower in energy? Which is going to form more often? Well, we have similar situation going on here, basically the same thing. We have a similar site of instability here, basically the same thing. The difference is where the pi bond starts to form, because we know pi bonds that are substituted with hydrogens are not as stable as pi bonds that are substituted with carbons. So if we're looking at the energy diagram here, and we're comparing pathway A versus B, for the NaOH to pick off one of these protons, the NaOH and this compound would be starting at some energy. The reaction pathway for B would be going through a lower energy transition state because the pi bond forms in a more stable spot than up here. And the product that is produced would be lower in energy versus A. And I say product, I mean the intermediate, right? The intermediate that's produced after this transition state occurs, the intermediate would be the enolate. Right? I would have either this enolate or this enolate here. And just looking at the enolates, they don't really look different in stability, but they're in resonance with the major form where there is a pi bond. And if the pi bond forms in a spot where it's more substituted with carbons, it's going to be a little bit more stable. So both the intermediate, which is the resonance stabilized enolate, and the transition state on the way to forming that are lower in energy. It's going to happen more often through that pathway. So I expect what's going to happen here is the NaOH is going to pick off this proton. And it's going to form an enolate here. And as soon as that forms, since I'm adding it dropwise, it's not likely to collide with another molecule of that and attack it. And since this has already been added with the NaOH, it's likely to attack the aldehyde. And so what that's going to form is, a number of these carbons here, 1, 2, 3, 4, 5, 6, 7, 8, and I won't number that, that's a terbutyl group. So carbon 1 and 2 are going to be the same. 3 is still going to have 4 and 5 and 6 and 7, but 3 is now going to also be connected to 8. And electrons are going to swing up to the oxygen from 8. And 8 still has a terbutyl group. So we'll just make sure we did this correctly. 3, 4, 5, 6, 7, 8 with the terbutyl group. So that would be the product after step 2. And the H3O plus is just there to protonate that oxygen. So we'll just draw that over real quick, a little bit nicer. If in step 3 I had added heat with the H3O plus, that would have made this more likely to leave. But since there's no proton here left to remove and create a pi bond, I wouldn't expect to see the alpha beta unsaturation. So if there were, instead of having 2 alpha groups here, if there were a proton here, the heat would pick off that, heat wouldn't pick off the proton, but heat would facilitate water to pick off that proton, swing electrons in and push out an H3O plus, and I would have a pi bond there. But that's definitely not going to happen. So there's no point in adding heat because of the fact that this carbon doesn't have any protons to be removed, so I can't form a pi bond there. So that would be the final product there. All right, so now we're getting into day 26, the content from last Wednesday. We talked about amines. And here I've got some amines, and we want to rank the pKa of their conjugate acids. Right, so we know the more stable the positive charge on these compounds, which are going to become ammonium salts, the higher the pKa. Right, pKa represents the strength of the acid. Lower pKa, stronger acid, less stable. Right, a strong acid is one that when you put in water reacts all the time because it's reactive, it's unstable, it's likely to give up a proton. Something will have a higher pKa if it's stable with the proton connected. So when I'm comparing compounds that are all neutral, it's hard to look at them and say, well, which is more stable? What we want to compare, or what we want to do here is to protonate each one of these nitrogens. That way, we can make a more fair comparison between how effective is this molecule at stabilizing its positive versus this, we already have picked up a proton, versus this positive, versus this one, versus this one. Right, so by comparing the stability of the positives, we can try to judge for each one of these, which one is going to have a more stable positive. The more stable it is, the less likely it is to donate the proton and go back. And the less likely it is to donate a proton, the weaker it is as an acid and the higher its pKa. So first thing I notice here is C. And And we talked about aromatic rings. We said an aromatic ring has to have 1, 2, 3, not necessarily 3, but it has to have an odd number of pairs of pi electrons to be aromatic. And we said when you have a ring and there's a heteroatom in the ring, like nitrogen or oxygen or sulfur or something, if its lone pair can exist in a p orbital that's overlapping with the neighboring p orbitals, since this is fully conjugated, if the lone pair on the nitrogen were in a p orbital, it would be able to overlap all the way around the ring. So if I have a flat ring with fully conjugated atoms, meaning all their p orbitals can overlap side by side, and I have an odd number of pairs of pi electrons, that's aromatic. So that compound is really quite stable. And if I pick up a proton, it loses the aromaticity. So this one's going to be very eager to donate a proton to something, keep those electrons behind, because without them, it's no longer aromatic. Without those electrons, if they're shared between the nitrogen and the carbon, this is an sp3 hybridized atom. So it doesn't have a p orbital overlap and create the resonance. So if you have a situation where it loses aromaticity by picking up a proton, it's not going to be, the equilibrium is not going to favor that happening nearly as much as it would otherwise. And so if the equilibrium doesn't favor the conjugate acid, that means the acid is stronger, it's more likely to donate a proton and go back. And so this one's going to have the lowest pKa. So that one is C. So C is going to have the lowest pKa of those four. The next thing that stands out to me is this lone pair here. Even though it's not making the ring aromatic, because even if I share that lone pair with a proton, I still have an aromatic ring. 3 pairs of pi electrons, fully conjugated ring that's flat. So the ring is aromatic in either way. So once this nitrogen picks up a proton, it's not like desperate to get rid of it, because even if the electrons stay behind, they're not necessary to make the ring aromatic. The ring's aromatic either way. But there is some resonance. So because these electrons can shift through a minor resonance contributor and shift onto the carbon, or onto that carbon, or onto this carbon, there are other minor but significant resonance contributors that no longer exist if the lone pair is now shared with a proton. So even though neither side is aromatic, so that doesn't really favor one side or the other, there is more resonance in the reactant than in the product. There's still resonance in the ring, it's still aromatic in the product, but there are other resonance contributors that involve that lone pair, and the nitrogen normally puts that lone pair in a p orbital so it can overlap and engage in that resonance. And if I rehybridize the nitrogen sp3 by making it share electrons with the proton, it does lose some of that resonance. So the fact that there's a little bit more resonance in the conjugate base than in the conjugate acid is going to help to shift that equilibrium toward the base side a little bit more than it normally would, which makes the acid a little stronger than it normally would. And so D is going to have a slightly higher pKa. So the pKa of C is going to be around 0 to 1. D, I think, is between 4 and 5. And when I look at A and B, their lone pairs are more available. There's no reason why A or B shouldn't be able to share that lone pair with a proton and stabilize a positive charge. So if I really want to analyze that thoroughly, I can go through the whole acronym. They both contain the same quantity of charge. Neither has any, in both cases it's the same atom holding the charge, a nitrogen. So C stands for quantity of charge, they both have a +1. A stands for atom, the positive is stabilized on a nitrogen in each of them, so that's the same. Neither has resonance stabilization before or after picking up the proton, so that's irrelevant. There's no significant induction to stabilize the positive. Now there is, in these methyl groups, a little bit of induction. And so the extra electron pair shifting there will maybe stabilize that a little bit through induction. So we can say this one is stabilized through induction. The orbital comparison is the same, so that's not a factor. So I'll just put induction here in red since that was a minor factor. And then the other thing is solvation. And solvation is pretty important. That's why I put it in the beginning of the acronym. It's usually a minor effect, but so are induction and orbital. And if we're looking at solvation here, what we see is these extra methyl groups are taking up a lot of space, blocking the solvent. Whatever the solvent structure is, whether it's usually in water when we measure pKa, it's going to have a negative end and a positive end. And that attraction between the solvent and the charge really is important to stabilizing it. And if it's blocked by these methyl groups all over the place, there's not going to be much of an attraction there to stabilize this. So if it's not very stable, it's more likely to shift back, which makes it a slightly stronger acid. So on an exam, I would probably expect you to recognize both the induction and the solvation are factors here. B's negative charge is a little bit more stabilized through induction because there are more methyl groups here to allow some electrons to shift in there through induction to help through the electronegativity difference to help stabilize the nitrogen. Yeah, these protons don't really shift much in, so they don't do very much induction, but these methyl groups do. So there's a little extra induction to stabilize B, but the solvation is really poor because of the methyl groups. So you could say in your answer that you think that B has a lower pKa because it's more likely to give up a proton because it can't be stabilized by solvation, or you could say A is more likely to have a lower pKa because its positive isn't well stabilized by induction, and so it'd be a little more likely to give up a proton and alleviate its positive. They're probably pretty similar, and so if you rank them either way, I could give you credit as long as you gave a good explanation and invoked the relevant factors that affect that. So I think in this particular case, the solvation is a bigger factor than induction, and so I would expect B probably be a little bit lower than A, but probably both of them are somewhere on the order of around 10 for the pKa. Questions about that one? All right, I've got one more here for us to look at. It's a synthesis problem, also involves using the nomenclature to draw a structure. So make sure you don't neglect too much your naming skills in your efforts to improve your synthesis skills. So here I want to first obviously draw the structure so I can know what changes need to be made here in the synthesis. So I've got prop, which means I've got 3 carbons. 1, 2, 3. I've got propanal. So obviously the exam will be typed. You won't have any issues with my penmanship, but this is an AL. And I've got a propanal, so that means I've got aldehyde presumed to be on carbon 1, right? The aldehyde ends the chain and nearly always takes priority over other groups, so it's assumed to be carbon 1 pretty much all the time. And that means on carbon 3, I've got a phenyl. So I need an aromatic ring here on carbon 3. So that would be the structure of 3-phenyl propanal. Over here, the the product I want to make is a pentane dial. So that means I've got 5 carbons and I've got a dial. I've got an aldehyde on both ends. So pent, because there are 5. Dial, because there are 2 aldehydes on either end, right? I can't put an aldehyde in the middle of the chain, or it wouldn't be an aldehyde, it'd be a ketone, right? So the aldehydes are presumed to be on the ends of the chain. So I've got some substituents here, obviously. I've got an ethyl on 4, and on 2 I've got a phenylmethyl. So remember, if you see groups in parentheses, the group that comes last is the one that's connected to the parent chain, and the number tells me where, and the one that comes first is connected to the one that comes next. Right, so I could list 3 or 4 groups here. You'd have to recognize the one that comes last is connected to the parent, and then the one before that's connected to that, and then anything before that's connected to that, expanding further and further out from the parent chain. We've got 2 groups here, though. The methyl is connected first, and then the phenyl is connected to that. And so now I'm seeing that this 1, 2, 3 phenyl group is the same here. 1, 2, 3. I'll just number it. 1, 2, 3 phenyl. 1, 2, 3 phenyl. So number it's a bond. So what I need to do here is somehow to get 2 to connect to this rest of the structure. So I'm going to change this numbering now. I got 1, 2, 3 phenyl, so I'll call this 4, 5, 6, 7, 8. So I've got to get carbon 2 to connect to carbon. Carbon I've numbered 4. And so that means I either make 4 a nucleophile and have it attack 2, or make 2 a nucleophile and have it attack 4. And what I see here is since 2 is connected, or alpha to a CO double bond, that's the site I'm going to try to make into an electrophile. Right, so just thinking here about how this might go down, if I take this original compound and I were to make carbon 2 a nucleophile by making it an enolate, what would I need for that to attack? Oh, I would need the other carbons here. So that's be 4, 5, 7, and 8, and then 6. And I want it to attack carbon 4. Can I just put a leaving group there? No, that's not going to work because it's going to attack there sometimes, it's going to attack here sometimes. Can I put an alpha beta unsaturated compound there? Maybe, but since this enolate is only stabilized through resonance with 1 oxygen, it's still a pretty strong nucleophile, so it's going to attack here sometimes and push electrons up to the oxygen, but it also is going to attack here sometimes and push electrons up to the oxygen. So it's going to give me a mess. So when I am in this situation, this is when I default to the Stork reaction. I recognize the feature of 2 carbonyls that are 5 carbons apart. That's a feature of the product of the Stork reaction. That's a feature of getting an alpha carbon to attack the beta carbon of an alpha beta unsaturated carbonyl. But if I want to do that cleanly without worrying about the alpha carbon attacking the carbonyl carbon directly, I need a nucleophile that's not so reactive, that doesn't have so much negative drawing it in to the site where the most partial positive is. So the first thing I want to do is to take the compound that I have that I want to make a nucleophile out of, and instead of making an enolate, I want to make an enamine. So my first step here is going to be to add a secondary amine an amine with 2 R groups and an H plus catalyst. And that will convert the aldehyde into, initially, my stomach is growling. Gotta finish this up quick. It will initially make an iminium ion, and then typically, since that's not very stable, another molecule of the amine will pick up this proton and shift electrons up there to the nitrogen. So that makes my enamine. I'm going to draw this like this. Just going to put pH for phenyl ring. Yeah, I'll draw it out. All right. So hopefully you can see how this structure here and this structure here are similar. The difference is they both have resonance, right? So, I mean, I can draw the other resonance contributor here where these electrons swing in and push these out to the carbon. And if I draw that, I'll have this resonance contributor. So both of these have a resonance contributor where there's negative on the alpha carbon, so they're both nucleophilic from that site. It's just that this is a minor resonance contributor compared to the major one because it has formal charges, and the major resonance contributor doesn't have any formal charges. So it's a much weaker nucleophile. Right, here's my major contributor, here's my minor contributor. In the enolate, the contributor with the negative on the carbon is still minor, but it's much more significant because when the electrons swing out to the oxygen, either way, there's a negative charge. So the carbon contributor with the negative is much more significant when the two contributors are similar in energy versus here where they're very different in energy because one doesn't have any charge at all compared to the other. So as we were saying, the enolate can't be readily controlled in terms of which carbon of the electrophile it attacks, so we don't want to make it. But the enamine is weak enough as a nucleophile that we would expect it to attack the beta site of an alpha-beta unsaturated compound. So we're going to get this compound, right? So just to recap where we're at so far before we move forward, we would start with the secondary amine and a little acid catalyst to make the enamine. In step 2, we add the rest of the carbons that we want this enamine to attack. We can draw that attacking from the carbon because the nitrogen would swing its electrons in and those would attack. Or we could just imagine the other minor resonance contributor having it attack. We want it, it's weak enough, and we expect it to attack the beta carbon, which is carbon 4. So we just make sure we get all our carbons in here. It's only a 5 carbon piece, probably not super expensive to purchase that. So when that attacks, these electrons will swing up to the oxygen. So this is the compound we would add in step 2. And so then the intermediate that would form there, we would have the nitrogen with the 2 R groups. This carbon here would bond to carbon 4, which is the beta carbon here. These electrons would swing over out to the oxygen. So just to number these to make sure we did it right. Never hurts to double check. I'll call this, well, keep our same numbering system. So 1, 2, 3 phenyl, 1, 2, 3 phenyl, and then over here we've got 4, 5, 6, 7, 8, 4, 5, 6, 7, 8. Good. So we've got our carbon skeleton now. We just need to make the final product. And so we would use H3O plus and water, and we would want some excess there so that the H3O plus can pronate here. When the electrons swing back in, it reforms our double bond, and the proton gets picked up onto carbon 5 because there was, oh wait, I didn't draw my pi bond in the right place. Oh, mistake. Carbon 2 will collide here, and these pi electrons end up between 5 and 6, not between 4 and 5. That's the second time I did that today. There we go. That makes more sense. So when these electrons swing in to make the pi bond between the carbon and the oxygen, these electrons will pick up a proton, and it will end up connecting to carbon 5. So that will create the functional group over here on this side of the structure. The H3O plus and water will also remove the iminium ion there and produce a CO double bond. We talked about that earlier, but let's just finish that off. I don't have much space, so I'm going to go this way with it. Oops, I need that. So first thing that would happen here would be a water attacking. Since this is already positive, it's not going to pick up an H plus. That would make it even more positive, but electrons would swing out there. I'm going to call this whole thing R, so I have to keep drawing it. So that whole thing, R, is connected to carbon 1, where now there's a water and a nitrogen. Now the electrons swung out there, so they're existing as a lone pair. So since this is unstable with a positive, a water molecule is going to pick that off. So that will make an OH there. And since we're using excess water, that helps push this equilibrium forward because all these steps are reversible. So then the nitrogen is going to pick up a proton. Making it positive. A lone pair here can swing in and push that out. And then a water can pick off this proton and form that group into the CO double bond there without the proton on the oxygen. So the Stork reaction, look at what we did here. We took a molecule without too many carbons. We added a bunch of new carbons. We got 2 new CO double bonds at a specific distance apart from one another. So there's a lot of increased complexity we added to the structure with only a few short synthetic steps. Any questions about anything we talked about today, or questions about anything in general? All right, well, I'm gonna go ahead and stop the recording then, since we're basically done. But if you do have questions, feel free to stay on.